Hello, good afternoon, good evening. I welcome you all to Tasking's joint webinar with partners, Wittgenstein and iSystems. My name is Bharat Kopa. I am a technical sales engineer at Tasking, and I will be the moderator of today's webinar. In the next 45 minutes, our technical marketing manager, Mr. Roger Smith, and our guest speakers, Mr. Felix Martin and Emiliano Costalli, will guide you through the safety aspects of SafeRTOS, and on how to develop an application using SafeRTOS on an Oryx using the Tasking VX toolset. And there will be a demonstration of iSystems debugger system timing profiling capability and analysis. Tasking is active partners with leading OEMs and tier ones, and we focus on safety critical cybersecure software development on multi-core architectures. Tasking provides a complete development environment that allows software engineers to develop reliable, functionally safe, cybersecure, and high-performance applications. Tasking provides tools that can be used in different stages of software development. The Tasking VX toolset consists of a compiler, linker, and locator, and simulation debugger, and they are all developed according to ASPICE Level 2. We provide a tool qualification kit with our compiler, linker, and assembler in accordance with ISO 26262, and this guarantees high tool confidence level for safety-related software development. The Tasking compiler also supports IEC 61508, along with the ISO 25119 for tractors and machinery for agriculture and forestry related applications. Tasking is offering an ISO 26262 qualified C and MAT libraries that support easy integration of model-based automated code generation. And the automated issue detectors built inside the Tasking inspector tool can help optimize your errata management, saving time and costs that arise from manual code verification related to safety software. Today's webinar will be recorded and will be available on demand. All our webinars are available in the resources webinar section on the Tasking website. And in case you have any questions or any questions come up during the webinar, please use the Q&A function of Zoom and type in all your questions, and they will be answered at the end of the presentation. So please use the Q&A option available in the Zoom. So let me introduce our speakers today. Roger Smith is our technical marketing manager. And before joining Tasking, he has over 12 years of experience developing applications related to braking, EPS, and passive safety. And Roger is with Tasking and working as a technical marketing manager for the past 2 years. Our guest speaker from Wittgenstein, Mr. Emiliano Costalli, is also a software engineer with extensive experience in developing real-time embedded software. And after graduating from the University of Pisa, he has worked with real-time operating systems, digital signal processing, and video processing for more than 15 years. Our guest speaker from iSystems, Mr. Felix Martin, is a systems engineer with exclusive experience in AUTOSAR profiling and timing analysis, and he helps engineers understand and optimize runtime behavior of embedded systems using techniques like software and hardware tracing. So with this short introduction, I would like to hand over to Mr. Roger Smith.
Thank you, Barath, for the kind introductions. I'd like to also extend a special welcome to our special guests from Wittgenstein and iSystem. Automotive systems development and safety go hand in hand. Terms like fault tolerance, ASIL compliance, fail operational, AUTOSAR, MCAL, freedom from interference, secure boot and data are commonly referenced when discussing automotive software requirements. But what about software development in other vehicular industries? Do the same terms apply? In the following slides, we will examine the need for safety in the CAV market and how developing non-AUTOSAR software still requires an RTOS for task scheduling. What is the CAV market? So CAV stands for Commercial Construction and Agricultural Vehicles. We see here a common piece of agricultural equipment used for harvesting grain. At first glance, the scene seems innocent enough. However, if we add a few unsupervised children, a couple of pets, and some field workers taking a break or listening on headphones, we have a potential safety concern. ISO 13849 addresses safety concerns in the CAV market by specifying architecture and high diagnostic coverage requirements. Here we see a simple flow diagram for a power takeoff switch. The power takeoff switch is a switch which ensures that drivetrain torque is not switched to the propeller blades here before we ensure that both the vehicle and the surrounding environment are in a state for safe operation. If we look a little more in detail here in the flow diagram, what we'll see here is a process for ensuring that the vehicle is in a safe operating state before we continue. So microcontroller 1 is going to first of all measure the seat load cell here to ensure that there's a driver present. We're then going to measure the shaft speed sensor and the torque sensor here to make sure that it is in a safe state. Notice that a second microcontroller is going to do the same measurements, and assuming that we have plausibility checks on all of our sensors and that the two readings agree, we're going to send a data good to our programmable logic device. To ensure additional safety, we're going to introduce a time of flight camera into the cockpit here to ensure that it's actually a driver that's sitting in the seat and not a heavy lunchbox or some other farm implement, which is registering a reading on the load cell. Now, assuming that all of these measurements are good, at that point, we will then enable the power takeoff switch and we will, the blades can begin spinning. So engineers are constantly seeking to implement smaller solutions that are also lower cost. And so what we're going to examine today is replacing this dual discrete microcontroller and PLD architecture with a single multi-core controller like the Infineon TC29X. We all recognize Infineon as a leader in automotive semiconductors. But did we realize that they are also very active in the CAV market? As we see here, some additional examples of vehicles which fall under the CAV setting or the CAV the CAV vehicles, sorry. So we have commercial vehicles, we have construction vehicles, and we have agricultural vehicles. So Infineon is actively developing silicon to resolve the challenges of electrification, safety, and security. If we look a little bit closer into the agricultural market and the CAV vehicles, in the CAV vehicle workspace, we'll notice that agricultural machines are still primarily non-automated, non-electrified, and non-digitized. Furthermore, the biggest culprit of the increased greenhouse gas emissions are non-road mobile machinery. Legislation is constantly being enacted across the globe to increase regulations for pollution and noise control. And the goals of these regulations are increased productivity and efficiency, as well as increased operator safety and comfort. These same challenges of electrification, safety, and cybersecurity also relate or face the automotive industry in general. So when we look at the idea of electrification, the target benefit is to reduce fossil fuel dependency, reduce CO2 emissions, and increasing efficiency and productivity. And this is we're investigating or currently things like mild or full hybrid implementation, replacing the diesel or gas internal combustion engine are being studied by engineers. If we look at safety and ADAS, we're going to examine two different vehicle classes within the CAV market. If we look at the commercial industry in terms of safety, many features like trailer roll stability, autonomous emergency braking, anti-jackknifing, lane departure warning, and enhanced night vision are being looked into. And if we look at ADAS in relation to farm equipment, we're looking at the increased automation of these implements. And the reason that we're doing this is for precise and fast operations, continuous operation of this equipment regardless of what the climate conditions are, and also adding navigation and GPS to create fully autonomous equipment. And then if we look into the connectivity and security area, we're seeing what we need to do is implement this cybersecurity to prevent sensor spoofing, as we're seeing more automatic steering being introduced into the CAV market via the usage of drones. And this is to allow more precise control for monitoring and spraying, irrigation, and soil analysis. And the types of sensors that are used in this technology are camera, ultrasonics, and 3D maps. So we're going to focus specifically on the Infineon AURIX microcontroller. So as you see here, the AURIX addresses these CAV challenges with its multi-core technology. It's very scalable families here. So we have cores that can up from 1 to 6 cores, frequencies that can up to 300 megahertz, and memory footprints, which can include up to 16 megabytes of flash and 7 megabytes of RAM. We'll see here the adding of, or the introduction of high precision floating point units for that efficient floating point calculation math that's required. We have the AURIX has a full platform safety concept, complying to both ISO 26262 and IEC 61508. And also a full set of software development tools, including the tasking embedded software development portfolio, the iSystem debugger, and the Wittgenstein RTOS. So the main point of the AURIX here is introducing its holistic safety concept. With its superior lockstep CPU technology, it proves to be much more than just a microcontroller with a safety island. If we look down here at some of the added hardware features here, safety features that have been added to the AURIX, we'll see here that the AURIX allows safe separation of cores, memories, and peripherals. Each core has its own memory protection unit, which ensures freedom from interference and data in both the data and resource domain. The register access protection allows static assignment of peripherals to specific cores. So you can restrict the access of those peripherals so other cores can't access them. So depending on your safety case. The detection of hardware faults and logical errors is crucial in order to meet the diagnostic coverage requirements of ISO 13849. And the SMU allows for flexible configuration of the reaction to a fault for advanced escalation and logging strategies. In general, the AURIX provides a high performance, memory scalable solution with robust peripherals and connectivity without the traditional safety shortcomings of multi-core devices due to its 26262 compliance. So now that we've talked about our CAV embedded system, we've talked about the heart or the brains of our system being the AURIX microcontroller. Even though the AURIX, as we saw, is very flexible, it's still considered a resource constrained device and thus requires an embedded operating system. So when we look at the 3 main types of operating systems, which are typically used in embedded software development, the first would be the superloop. And in this idea here, there's a background region which contains tasks which are to be executed sequentially. When an interrupt is triggered, the background tasks are preempted. Software will switch over to the interrupt service routine in the foreground. This type of implementation can be unpredictable, so it's not used really in safety applications. The next idea is the cooperative scheduler, which works much like the superloop scheduler, except that the tasks are grouped by time slots. They will run only when their particular time slot is active. And in principle, this type of scheduler is more organized and more deterministic than a superloop. However, in safety applications, determinism is paramount. In order to achieve safety and determinism, our AURIX device still needs a certified multi-core RTOS to utilize its vast number of hardware features. So thus an RTOS kernel or scheduler is required for managing all the tasks in our system. To go into more detail on this topic, our guest from Wittgenstein, Emiliano, will explain this in more detail.
Thank you, Roger. So I'm going to talk a bit about SafeRTOS on a Oryx platform. SafeRTOS is a real-time operating system for safety critical applications. It has been pre-certified according to ISO 26262 as an ASIL-D software component, and with IEC 61508 as a SIL-3 component. You can see the portfolio of SafeRTOS services and features. Apart from the source code, SafeRTOS is shipped, can be shipped as a design assurance pack containing the evidence of the development and testing that is can be used to make a safety claim. On top of that, we also provide some middleware in terms of TCP/IP stack, other optional safety components, and debugging tools that they are also available. And in addition, we also provide support and training on demand. So what are the SafeRTOS features? SafeRTOS is basically a responsive, priority-based, preemptive task scheduler. It's priority-based, but tasks of the same priority are scheduled in a round-robin fashion, basically with time slicing, one tick per time slice. Communication between tasks and ISRs can be implemented using queues, semaphores, task notifications, and event flags. Software timers are also available to perform operations, to schedule individual operations in the future without creating a task for each one of those. SafeRTOS also has self-test features, and runtime statistics are optional. And especially with SafeRTOS, it's possible to define memory protection unit regions on a per task basis. So each task can have its own. SafeRTOS source code is also compliant with MISRA-C, and the typical ROM and RAM requirements are 16 to 32 kilobytes of ROM and 1 to 2 kilobytes of RAM. This depends heavily on the compiler, the compiler optimization, and on the configuration. Indicatively, stack requirements are around 400 bytes per task to be able to use the SafeRTOS API. The list of safety standards that SafeRTOS have been developed according to for industrial IEC 61508, and for automotive it's ISO 26262, as we said. So what does SafeRTOS add to a project? Being according to ISO 26262 and ASIL-D component, it allows, it can be used in an ASIL-D application. It gives dependable and deterministic task scheduling as a real-time operating system. It is provided with a specific combination of processor and compiler. So it's already ported to the combination selected by a customer. The memory protection unit allows building memory blocks to assist the creation of spatial separation between tasks, which is useful with ISO 262 products. The evidence of development and testing followed by with SafeRTOS allows a smooth path to certification. Also, this support provided by Wittgenstein is handled by experienced engineers, which makes it easier to solve problems. The cost of ownership over product lifetime is low, and last but not least, Wittgenstein High Integrity Systems is a safety systems company, and it's part of a stable and mature corporation. So for automotive, what does SafeRTOS offer? SafeRTOS, as it comes as an ASIL-D pre-certified real-time operating system, which, so with the memory protection unit, as we said, it allows achieving spatial separation. Safe checkpoints are a optional component that will also allow achieving temporal separation, which is the other type of separation required. And optionally, we also have a OSEC adaptation layer, which can be used in some automotive applications. SafeRTOS is widely used across the automotive industry. So as we can see a typical diagram of a product using SafeRTOS. At the bottom, we have your chosen processor, also your chosen compiler applies to the whole project. SafeRTOS sits just on the chosen processor. It's made of two parts. There's a common part called core layer and a portable part which interfaces the core layer with the processor. The application will be developed on top of SafeRTOS, obviously sharing the same compiler. You can see on this slide a partnership network with both vendors of hardware and compilers. So a few more words about spatial separation using the memory protection unit. The memory protection unit is used to prevent unauthorized access on memory regions within a memory map. So microprocessors that have a memory protection unit typically allow a number of memory regions to be defined. The memory region is basically an address range with associated access permissions. Different memory protection units have slightly different features, but the one on the Oryx processors have an additive MPU system. So this means that when two MPU regions overlap, the overlapping part will inherit the access permissions from both MPU regions. What happens if an unauthorized access is attempted is that an exception will be generated. So some actions it will be possible to perform actions to address that problem. So we can see in this case, we have 3 tasks, each one with its own MPU configuration. Some of the memory regions of the MPU regions are common, are the same for each task. Typically the ones that protect the kernel code and the kernel data. So these are always protected and shouldn't be accessed by any task unless they go via the API. And some regions can be shared between tasks. To do that, the same regions are programmed on the tasks sharing the region. So you can even have one task with only read access on a region and another task with only write access to the region. Obviously, private regions are only programmed on one single task. The other type of separation is temporal separation. This can be achieved using checkpoints, which are an optional feature. Checkpoints are a type of software task-based watchdog. So it's possible for each task to specify a minimum and a maximum frequency of execution. In this case, you can see that a low priority task in the middle, every time it is executed, it will reset the checkpoint, its own checkpoint, with, in this case, minimum 45, maximum 55 tick period. So if the task is executed the next time before 45 ticks or after 55 ticks, then this will be considered as an error. And in this case, a error handler will be executed. So the host application is able to specify, to provide an error handler to handle the problem. Obviously, every time the task is executed, this checkpoint is reset, so the counter starts from 0. Last, asymmetric multiprocessing is supported by SafeRTOS, where on the same processor with multiple cores, a different application, SafeRTOS-based application, can be executed. The SafeRTOS API allows not only inter-task and task-to-ISR communication within the same core, but also communication between multiple cores running SafeRTOS applications. What this is achieved by using the stream buffers, which is the a recent feature of SafeRTOS version 9. Stream buffer is basically a FIFO circular buffer where one core can write data to and another core can receive data from. This allows data to be exchanged between cores in case the application requires. So this is it from about SafeRTOS. So I'm giving Roger control back.
Thank you, Emiliano. So in order to analyze the synergies between the RX microcontroller, the Tasking VX toolset, and the Wittenstein SafeRTOS, a demonstrator was created. The hardware is shown here, and it was based on a Redline development kit from Neutron Controls. This current implementation here uses the TC29X. And first and second generation RX devices are supported. So all you'd have to do is basically get a 3.3 MCU module here to support that microcontroller. You can see here the different pieces of the system. So we have the main kit, we have our power supply, dual communication here via the ASCII LIN peripheral of the RX, and we have a BLDC module board here. Primarily, we're using it for the potentiometers for the A to D functionality of the demo. What you can also see here is that both the Infineon Mini Wiggler can be used to support the tasking embedded debugger, as well as the iSystem IC5700 debugger. It will also should be noted here that this hardware is planned to be extended to support the TC4X as silicon becomes more readily available later in the year. So if we look at the demonstrator software, the software was based on a previous version of the Wittenstein SafeRTOS demo code release. So this particular demo that we'll be looking at today is based on version 7.3.1. And this demo code release has been heavily modified to showcase the best-in-class multi-core capability of the Tasking Tri-Core VX toolset. So some of the features that have been added is we took advantage of that dual communication interface to add support for a command line interface and debug windows. We're now able to operate in either a shared, private, or cloned memory context. And this is something that we will talk about more in the next couple of slides. We've realigned the MPU memory overlap and developed new port trap handlers to allow independent multi-core applications. And then we've also implemented some inter-processor communication using hardware semaphores and added support for OS-aware debugging. So here you can see there were 3 key SafeRTOS features, which were instrumented, say, fully in the demo, so that a user of the demonstrator can actually get a better feel for how the features work. And here you can see an example here of the suicide task. Based on time constraints, I will not go through this in more detail. So what we're going to do now is we're going to look at a couple of the features, multi-core specific features of the tasking tool set that were taken advantage of and implemented during this demo here, or for this demo. So some specific assembly instructions have no equivalence in C. And so for these instructions, intrinsic functions were created for the tasking tri-core compiler. These are atomic operations, and an atomic operation is a function that is basically allowed to execute completely without being interrupted. And so 3 of these easy to use RX atomic intrinsic functions were implemented or utilized within this demo. And I will point out that our compiler will always inline these atomic intrinsic assembly instructions rather than calling them as a function. And this avoids parameter passing and register saving instructions so that these operations are very quick and very efficient. So the first 2 that we used were swap under mask and load modify storage, which we'll look at in more detail in the next slide. And then the third intrinsic function that we utilized was called the compare and swap function. And this function basically locks all other cores from accessing a critical function until that function has completed its what it's trying to do, and then that function will then be unlocked. So if we look at more detail, when the RX enters reset, core 0 will start up. And during the startup routine, you'll see like the declaration of data types, we'll define the starting label, we'll set the address of the other cores which are available within the RX. And so since we're using a TC29X in our example, there's 3 tri-core cores. And so TC0 will do the first startup, and then TC1 and TC2, the starting address will be specified. And then the other features that occur are for setting up the target processor. So you'll see, special function registers are processed. We'll set up the user stack pointer, watchdog timers, trap vector table, interrupt vector table. And so the C start code that's provided by tasking does all of this automatically for you. It sets up the context save areas. And then it implements the copy table or initializes global variables. And you'll see here after we start the address of TC of core 1, we're going to clear the halt flag, which basically starts the startup routine for core 1. And then we do the same thing for core 2. Now in these start files here, it's much more processor specific. So you won't see like general clock configuration and memory configuration happening in these routines. So what you can imagine now is that we have 3 sets of start code running in parallel. And simultaneously, each one of these startup routines is processing the system copy table for variables associated to their specific core. You can also probably imagine that the number of variables associated with each one of these cores is not equally distributed. So the startup codes will not finish at the same time. The last thing that we want to have happen is to have the winner immediately start processing its associated application, while variables in the other cores which aren't ready yet aren't initialized, and this could lead to erroneous behavior. So what we've done here in our example or in our use case is that we've created a global variable And what that global variable does is it takes advantage of one of these atomic intrinsic functions. And the goal is to wait till each one of these cores is properly initialized before we continue operation. So you can see here when core 0 has been properly initialized, that our atomic intrinsic function will basically set this particular bit within this global variable that all of the cores can access to say that it's ready. You'll see a similar behavior from the other 2 cores. And so once all 3 of the cores are initialized correctly, our key is met. And then what we're going to do is we're going to take advantage of our other atomic intrinsic function to basically clear the halt and let all of the cores basically come up and run. And now we're going to access our main application. So what we've seen here in this example is that the use of these atomic intrinsic functions have ensured that all 3 of our cores were started before starting the scheduler. And this was necessary to implement in order to get stable operation, mainly with the IC 5700, because what we were seeing previously to implementing these instructions is that one core would start running and then the other core wouldn't, and then that would basically we would lose track of our state of our the operating of the demo. So the other multi-core feature that I want to talk about are cloned or core associations. And so what tasking does is we support compile time core association, and this allows us to run your applications in different memory contexts. So the first would be in a shared context, and in this context, all code and data would be accessible by all cores, and all the symbols would be shared in memory. There's a private context, and in this case, the code and or data is copied to and accessed from the local scratch pad of only one core. And then the cloned core association is code or data is copied to the local scratch pad memory of each binary compatible core or a specified core. And then the core treats that code or data as if it were private. And so what we're going to do now is we're going to go through an example of the cloned and private core association that was implemented, within the demo to give you a better feel of how this works. So you can see here, this is a very simplified view of the TC29X. So as we've mentioned previously, there's 3 tri-cores here that are available within this RX family member. And then I've also shown here a little snippet here of the 29X memory map. And you can see here that tri-core 0 has local scratchpad RAM. So there's data RAM and program RAM that is really close to this core or internal to that core for optimal performance. And you can see the address range here. Likewise for core 1 and core 2. You also have scratchpad RAM and program scratchpad RAM at these addresses. Okay, and then you can also see here, up here in the upper address range, we have internal access for DSPR and PSPR, so data scratchpad or program scratchpad. And this is, and you'll see in the example how our core association takes advantage of the RX architecture. So when deciding whether you want to use cloned or private and shared, there's a number of key application considerations. The first is your data object going to be accessible from 1 or multiple cores. 2 is, how many memory instances of a particular data object do you need? What type of memory are you trying to use? And as previously mentioned, this use case will look at a timer struct, which we created or which was used inside of the demo. And we'll look at the differences in code implementation and what actually happens in memory for both the cloned and private compile time association. So let's just, we'll just put our picture of our RX in here for reference. And there's a little bit of an eyesore, but you can see here that we're using cloned here. And what we've done here with this clone volatile is we've set up a simple timer here, and you can see that the timer takes up 20 bytes. So we have five 4-byte members, and you can tell that by looking at this illustration from our map file. So you can see here that the size is hex 14 or decimal of 20. And the key thing here that you'll see is that by this simple piece of code, what we've done is we've created the exact same timer in both our DSPR0, our DSPR1, and DSPR2 memories. You can see that down here that we have our core 2, our core 1, and our core 0 snippet from the memory map. And you can also see here that each one of these timers has the same base offset into that local memory. So it makes it really easy to manipulate and work with these timer structs. If you look over here at the private implementation, you'll see for the private implementation, we had to specify the core 0, the core 1, and the core 2 through our private instruction here. And you can see also that, now instead of just calling it timer driver, we've had to call it timer driver 0, 1, and 2. So it's a little more, a little more code. And then taking a look here at the map file here, you can see we got lucky to have all of the base offset addresses be the same. But, at different times during the development, based on the order of commands, we saw different offset addresses into each one of these local scratchpad memories, which just made it a little more cumbersome in order to deal with the timer. So if we go and we look at a little more detail when we're actually running the debugger, we'll see that this particular tick count struct member had a value of 150,000, which when you convert that to hex, you get the 249F0, and you can see that is created in memory. But you'll see that with this core association detail, that it's automatically cloned in each one of the local RAM, in each one of the local scratchpad RAMs. Likewise, if we move through operation, we'll see that the 001 is also created here. Likewise, and then the 00 and the 01 are also created here. You can see the first 00, the second 00, and then the end 01. So again, very easy to work with this timer in this cloned model. When you look over here at the private implementation, you'll see the same data is created. However, you'll see the specificity here of timer 0. You'll see, if we continue on, the specificity of the timer 1. So again, the information is contained, within the correct scratchpad RAM at the correct address. It's again just a little more cumbersome. If we look at this drawn out view here, you can see this is all the code that was required for the cloned implementation versus the private implementation. And if we zoom in a little bit on the private implementation, you can again see that we're talking about specific timer 0 values here versus timer 1, versus here the STM for 1, the STM for core 0, whereas over here you don't have to worry about any of those details. Keep in mind again that this was for a struct that we were putting into multiple memories, and so of course the cloned core association made the most sense. But you can imagine if you were trying to keep some freedom from interference from your data in memory, that you would then, the private core construct would be more useful for that type of implementation. And so now I'm going to pass it over to Felix, where Felix can go through the iSystem debugger and how when he analyzed this example, what he was able to discover.
All right. Yeah. Thanks so much, Roger. So my name is Felix. I work for iSystem. We make universal debug and trace tools. So universal here means that our tools are microcontroller agnostic. For example, we support the Infineon Oryx architecture, but we also support other microcontrollers like the Cortex-M-based Infineon Bravio 2 microcontroller. But we also go beyond debugging and tracing. We really try to help our customers with advanced analysis of the embedded systems. So for example, we can handle use cases like capturing program flow and correlating that with task state data. So RTOS awareness, network traffic analysis, analysis of GPIO states, and many more use cases. And we also have a global support footprint. So for example, I'm located in the US. We of course have support in Europe, based out of Germany, and of course also for China and India. So I want to talk about two things. First, I want to give an introduction into our tools, and then I want to go into a little bit of detail when it comes to, with regards to SafeRTOS and SafeRTOS awareness and the use cases that we can cover for a SafeRTOS based application. So our tool portfolio consists of the hardware side and the software side. So to do hardware debugging, you need a way to connect to the target, and then you also need a graphical user interface that connects to the debugger and enables you to debug. So I will cover these two parts here. So first, with regards to the debugger hardware, our flagship product is the IC5700 that Roger has already mentioned. In addition to the IC5700, we also offer so-called add-on modules. So here you can see one for analyzing CAN and LIN network traffic, and one for communicating or analyzing digital or analog pins. And you can do both of these use cases either statically while debugging, or dynamically while tracing. And then lastly, here on the left side, I also want to mention a little bit an advanced feature maybe. So in certain domains, for example, in steering or braking in automotive, especially when we go into autonomous driving, you might have requirements, safety requirements that require redundancy. So you might have two microcontrollers that are running the same application and then cross-checking each other. So we have customers who deal with such systems, and to support them, we have implemented what's called synchronized debug and tracing. So in this picture here on the left side, you can see two Infineon Oryx microcontrollers, and they can be debugged and traced synchronously. So that means if you set a breakpoint on one of the microcontrollers, the other one will stop, and you can see what the other core was doing. Similarly, you can also record a trace on one microcontroller and trace at the same time on the other microcontroller, and our tool will automatically synchronize and correlate those two traces. So then you can do, for example, event chain analysis, and we will talk a little bit about event chains in a second, but you can do that over multiple ECUs. Of course, in addition to the hardware, you need the GUI. So this is WinIDEA. That's the GUI that comes with our blue boxes. It has all the features that you would expect from a modern IDE. It actually has a built-in project manager. So if you so desire, could build your application from within WinIDEA. And then you can, of course, set breakpoints on source code level and also on disassembly level, seen on the right side. You have a call stack that shows you the nesting of your functions when you hit a breakpoint. Moreover, there are different ways to access memory and variables. So we have talked a little bit about like special functions that the Oryx provides. For example, the memory protection unit. So if you want to double check the configuration of your memory protection unit, for example, you have the special function registers view that is seen on the left, where you can dig into these registers and analyze your configuration. We also have the memory view on the right side that gives you like kind of a raw picture into the memory of your Oryx. And then lastly, of course, there are also watches that can be either statically configured, so when you hit a breakpoint, all the values are updated, or of course, there's also a real-time watch that updates while the application is running. So those are the generic features, and now I want to talk a little bit about SafeRTOS awareness. So Emiliano has mentioned a couple of advanced RTOS synchronization mechanisms that are available for SafeRTOS to manage the behavior of your application. So to give you insights into like what these mechanisms are doing, we have a couple of plugins, as you can see here. So first and foremost, we have this task status plugin that shows you the tasks in your system, their priority, their current state, their stack and stack usage. And then in addition to that, we also have support for semaphores, queue objects, and timer objects. So these plugins work, can also be updated in real time, or when the application is stopped, you can analyze the current state of these objects. So now to make it a little bit more interesting, we can add hardware tracing into the mix. So hardware tracing is a technique for recording data and program flow trace data while the application is running. And the nice thing is when we have data trace available, we can use that same information from the SafeRTOS task state plugin, and we can trace the respective variable to reconstruct the dynamic behavior of the task states. And this is what you see on the lower screenshot here. So if you imagine on the x-axis, you have the time, and then over time, you can see which of the different functions in the systems are running. And based on that, you can then do a whole type of different types of analysis. So for example, you can check the net execution time of your different functions. You can make sure that requirements are not violated so that the net execution times don't exceed a certain value, and so on. Of course, you can also calculate statistics, and that allows you, for example, to see the load that is caused by individual functions. You can also make sure that the activation period of a function is within a certain range. So you can make sure that your 10 millisecond task is really executed every 10 milliseconds. And then you can also go beyond statistics. So for example, you could calculate the CPU load over time, as is shown here on the upper part of the screen. Maybe one thing that is interesting here that we notice is usually the way that you calculate the CPU load is by first measuring the load of the idle task and then calculating 100% minus the load of the idle task. And it's interesting here that the idle task never executes, as you can see on that screenshot in the middle. And that's because the GUI, the application developed by Tasking, has this command line interface hook. So there's actually a little terminal that you can use to execute different commands. And that CLI hook is always active. So the idle task never has time to execute. So in this case, we could kind of use the CLI hook as our idle task. And then finally, I've mentioned event chains before. So event chains are really interesting technique for analysis. So the canonical example here would be if you have an application, let's say a brake assistant application, and maybe you have some camera data that you gather, and then you process the camera data, and based on the result of the processing, you want to make a decision if emergency braking is necessary or not. So if we have task-based analysis and this dynamic view of what the application is doing, we can analyze such event chains. For example, here on this screenshot, this kernel timer manager occasionally triggers this notify task. So as you can see with these black lines, that's a so-called event chain. So it gives us the time from the kernel timer manager to the notify task. And similarly, if we have a more complex event chain like the one that I've just mentioned for the braking system, you can specify that and then analyze it in the Vinadier trace view. Okay, and with that, I want to conclude my part of the presentation and give it back to Roger.
All right, thank you, Felix. So as we wrap up our discussion here, some key points for you to remember. The first is that the RX provides a holistic safety concept through hardware features that ensure multi-layer access protection for memories, peripherals, buses, and global registers. The second point is that SafeRTOS is a 26262 and IEC 61508 pre-certified real-time operating system that provides dependable and deterministic task scheduling and is available within OSIC OS wrapper and is widely used across the automotive industry. Tasking offers high-performing, high-quality, safety-oriented software tools that conform to ISO 26262 and IEC 61508. And tasking specializes in multi-core software development and provides unique features to take advantage of the RX architecture. And we examined in detail the atomic intrinsic functions and special memory contexts. iSystems WinIDEA is a universal debug and trace solution. And iSystem cooperates closely with semiconductor, compiler, and RTOS partners to ensure an efficient and powerful debug experience, including solutions for advanced timing analysis and reporting. So with that, if there's any additional questions here, just let you know we're here to help. So we've provided my Felix's and Emiliano's email addresses here. And also, if you're interested in learning more about tasking iSystem or Wittenstein high integrity systems, please visit our website. So with that, I'll hand it back over to Barath for closing remarks.
So thank you very much, Roger, Emiliano, and Felix for your interesting presentations. And I also thank the audience for your attention. And you can follow us on LinkedIn. Please have a look at the event sections on our website for more upcoming webinars and events. And in case you have any questions related to any of our products that were presented in today's webinar, or if you would like to evaluate any of these products, please write us an email at sales@tasking.com. And our representative will get back to you. And now it's time to move on to the Q&A. So I see some questions are popping up. So I will read out these questions and maybe our guests can answer or answer these questions for you. So the first question, what is MPU region? And could you please provide an example of task definition for MPU regions?
So Emiliano, did you want to take that one?
Yep. So can you hear me?
Yep.
Okay. So an MPU region is basically a memory range with associated permissions. Permissions could be read or write, for example. So an example of an MPU region would be made of a start address in memory, a size of the range, say for example 1 kilobyte, but it could be down to even just I think 8 bytes on the Oryx platform, and read and or write permissions. So for example, when you create a task, you can do that. You can specify a number of MPU regions this way, and every time the task is scheduled, it will be these permissions will be applied.
Okay, thank you very much. So then we have another comment. Can we see the recording of this later? Of course, yes. So we will upload this webinar on our website. So make sure that you visit our website and you can see this webinar on demand. Let's move on to the next question. I think this is also for Emiliano. Is SafeRTOS compatible with IAR compiler?
Yes, it is.
Okay.
Simple answer.
Yeah, and then another one for you. Where to configure these checkpoints in SafeRTOS?
So each task or even each ISR interrupt service routine can have its own checkpoint. So each task will create a checkpoint object specifying a number of parameters like minimum, as we've seen on the slides, minimum and maximum execution period, and also whether you want the checkpoint to be a single shot or we want to be periodic.
Mhm.
So you configure it like that when you create it, and then on each task, when the task is executed, it will call an API function to reset the checkpoint, to reset the counter on the checkpoint.
Okay. So I hope that's clear. So let's move on to the next question, and I think it could be for Roger. Clone variables are instantiated for each core, but they can be set to different values in each core. They are not mirror images of each other always. Is this correct?
Yes, that is correct. So when you initialize or when you set up your timer struct, the initial settings were kind of cloned or into each one of the local scratchpad RAMs. However, you could also now have private functions, say for instance, or you could have a wrap type function where you only access have a specific core, only want to access a specific timer, and then he could then set up a private instance or a private function and then access and modify that particular timer value. So that is correct.
Okay. So the next question again for Emiliano, does the temporal separation checkpoint feature come with the SafeRTOS kernel?
Yeah, it's optional. So it's a plugin of SafeRTOS. It's not strictly speaking part of SafeRTOS default SafeRTOS form, but it can be added on demand.
And is the SafeRTOS now available for TC3X processors or just TC2X?
It's available for both TC first and second generation Oryx.
Okay. So stream buffers for task synchronization are available in SafeRTOS version 9.x. How can we properly implement the same features with SafeRTOS 7.x?
You need SafeRTOS version 9. It's part of the API of SafeRTOS version 9.
Okay. One more, is the TCP IP stack included in the SIL3 pre-certified software, or will it have to be running in a different safety partition?
Yeah, it's not. It's a commercial grade feature, so it's not validated. It's not part of the SIL3. Yeah, we'll have to run on the not on the ASL partition, on the SW partition.
Okay. Is it safe to run unsafe third-party code and SIL3 code on the same MCU when using spatial and temporal separation?
It is possible. The host application needs, and the host application developers need to make sure that no paths can be established between the two partitions that could compromise separation. But SafeRTOS offers the tools to implement that. But ultimately, it's up to the host application developer to apply these tools and to make sure that the separation is guaranteed. Okay.
So now I think this will be a question for Felix. System timing analysis feature with the iSystems debugger. Do we need a special hardware for this?
Yeah, that's a good question. No, don't need any special hardware in terms of the debugger, or you need your debugger and the
Felix?
already. Oh, so yeah, here I am. Sorry about that. Yeah, 2 years into work from home and I still cannot unmute myself. Anyway, that's a good question. You don't need any specific hardware in terms of the debugger. However, you have to make sure that the microcontroller that you're using is trace capable, so that it has like that special part on the silicon that is required for hardware tracing. And then on some microcontrollers, you have a dedicated trace interface. So for example, on the Infineon Oryx, the standard interface is the DAP interface. So you can record traces via that without need for any additional specific hardware. And then you also might have what's called a high-speed HTTP or Aurora interface. And if you had that interface, then you would need a specific adapter for that. But yeah, in general, you don't need any different or special hardware from iSystem. The regular debugger is trace capable.
Okay, thank you very much. So I think this will be a question for you, Roger. We are currently developing an application with TC39X and using the tasking compiler. What is the plan to support TC4X?
That's a great question. So Smart Code, our newest compiler, has just recently been released, and that does support, that will be a ISO compliant tool set as well, and it will support the TC4X, and it will support cross-linking between the TC3 3X. So I think that, hope that answers the question.
Okay, so I think I will have to get back to Emiliano again. I get RTOS not loaded when using FreeRTOS plugin in WinIDEA. What could be causing that, or is it a question for Felix?
Yeah, I think that's for me probably. Yeah, so there are two things to check. First, like if you, I think you said or wrote FreeRTOS. So we have like different plugins for FreeRTOS and SafeRTOS. So the first thing would be make sure that you use the right plugin for whatever operating system you're using. And then if you still get that error, we probably would have to look into it, what's going on. So in that case, you can write to support@isystem.com, send them the error, and then we will have to look into it. Yeah, but the first thing is to make sure you use the right plugin for either FreeRTOS or SafeRTOS, depending on what you're using.
Okay, thank you, Felix. Another question, is LDMST instruction good to use compared to directly writing variables to a variable, values to a variable? How it benefits in multicore?
So it is a since it is an intrinsic function, it is a function that cannot be interrupted, and so it is something that once it is started, you know, it will run to completion. And so an interrupt or a bus access or any of those types of things happening inside of your Oryx will not interrupt that particular instruction. And then the other thing is that instruction is accessible by all cores. So if you have, you know, like a 3.9, all 6 cores can basically implement that function.
Okay, so another question, what does return value of swap function the tasking specifies? I think the question is more related to the function __ swap, return value of swap function by tasking. So should we take this offline maybe?
Yeah,
so I have like a small code snippet. Yeah.
Yeah,
okay.
yeah. Let's take that offline. Yep.
Okay, so then we will take this question and get back to you. We will write back an email to you. So if there are any more questions, so please use the Q&A option in the Zoom and write to us. Our speakers will be happy to answer these questions. Okay. Looks like we have no further questions. So I would thank you all for your participation and for your time. And as already mentioned, the webinar will be uploaded on our website, and you could watch it on demand. And if you have any further questions, please contact our guests, the speakers of today's webinar, or write back to us at sales@tasking.com. With this, we would like to end this webinar. Thank you again, and have a nice day.
Thank you.
Thanks. Bye-bye.
Goodbye.